1.6 Electron arrangements and ionization energy. The patterns in first ionization energies across a period provide evidence for electron energy sublevels. Electrons can be removed from atoms, and the energy it takes to remove from them can be measured. This is called ionization energy because as electrons are removed, the atoms become positive ions. Ionization energy is the energy required to remove a mole of electrons from a mole of atoms in the gaseous state and is measured in kilojoules per mole. Ionization energy has the abbreviation IE. You can measure the energies required to remove the electrons one by one from an atom, starting from the outer electrons and working inwards. The first electrons need the least energy to remove it because it is being removed from a neutral atom. This is the first IE. The second electron needs more energy than the first because it is being removed from a 1+ ion. This is the second IE. The third electron needs even more energy to remove it because it is being removed from a 2+ ion. This one is third IE. The 4 needs yet more, and so on. These are called successive ionization energies. For example, sodium, Na. In first ionization energy, you have Na at the beginning on the reactant side, and on the product side you get Na plus 1 electron, which is first IE, and produces 496 kilojoules per mole, whereas second IE, where you start with Na plus and get as products Na2 plus and 1 electrons, second IE, produces 4,563 kilojoules per mole. And third ionization energy produces 6,913 kilojoules per mole. Notice that the second ionization energy is not energy change for Na on the reactant side, which then turns into Na2 plus 2 electrons. The energy for this process would be first ionization energy plus second ionization energy. If you plot a graph of the values shown in table 1, you get figure 1. Notice that 1 electron is relatively easy to remove. Then comes a group of 8 that are more difficult to remove, and finally 2 that are very, very difficult to remove. This suggests that sodium has 1 electron furthest away from the positive nucleus, which is easy to remove. 8 electrons nearer into the nucleus, harder to remove. 2 electrons very close to the nucleus, very difficult to remove because they are nearest to the positive charge of the nucleus. This tells you about the number of electrons in each main energy level, or orbit 281. The 8 electrons in shell 2 are in fact subdivided into 2 further groups that correspond to the 2s2 and 2p6 electrons in the second main level, but this is not visible on the scale of figure 1. It is just visible in figure 2, which takes a logarithmic scale. You can find the number of electrons in each main level of any element by looking at the jumps in successive ionization energies. The trends in first ionization energies moving across a period in the periodic table can also give information about the energies of electrons in main levels and sublevels. Ionization energies generally increase across a period because the nuclear charge is increasing, and this makes it more difficult to remove an electron. The first ionization energies of the elements in period 3 in kilojoules per mole. Na 496, Mg 738, aluminium 578, Si 789, P 1012, S 1000, Cl 1251, and Ar argon 1521. Plotting a graph of these values shows that the increase is not regular. In going from magnesium to aluminium, the ionization energy actually goes down despite the increase in nuclear charge. This is because the outer electron in aluminium is in a 3p orbital, which is of slightly higher energy than the 3s orbital. It therefore needs less energy to remove it. In figure 3, notice the small drop between phosphorus and sulfur. In phosphorus, each of the 3p orbitals contains just one electron, while in sulfur, one of the 3p orbitals must contain 2 electrons. The repulsion between these paired electrons makes it easier to remove one of them, despite the increase in nuclear charge. Both these cases, which go against the expected trend, are evidence that confirms the existence of S and P sublevels. These were predicted by quantum theory and the Schrödinger equation. Figure 6 shows that there is a general decrease in first ionization energies going down group 2, and the same pattern is seen in other groups. This is because the outer electron is in a main level that gets further from the nucleus in each case. Going down a group, the nuclear charge increases. At first sight, you might expect that this would make it more difficult to remove an electron. However, the actual positive charge felt by an electron in the outer shell is less than the full nuclear charge. This is because of the effect of the inner electrons shielding the nuclear charge.